In the last section of Chapter 9, we're going to be looking at geometric series. So first, let's look at the sum of a finite geometric series. We're going to use this formula. Again, this one's going to be really important, so make sure it's highlighted, make sure it's starred. The sum of a finite geometric series would be a1 times 1 minus r to the n all over 1 minus r. So again, breaking down what all these variables mean, a1 is our first term, r is our common ratio, or what you're multiplying by every time, and n is your number of terms. So first, let's start out with a simple problem of just finding the sum of a finite geometric series. What is the sum of the following geometric series? We're starting with 3, we're going to 6, to 12, to 24, and ending with 3072. So first, to find my common ratio, I see that that's 2. My a1 value is 3. The only thing that I really have left to find is my number of terms, which again can get a little bit tricky. Here's how you could figure it out algebraically. I'm going to use my explicit formula here for a geometric sequence. So my nth term is my first term times r to the n minus 1. I'm going to plug in 3 for my a1 term, 2 for my r term, and I know that my final term, a sub n, is 3072. So now I basically have an algebra problem and I'm solving for n. And I know our n value or our variable is stuck in the exponent. We did learn a trick a couple chapters earlier of how to solve a question like this. What we'll want to do first is get that exponent value by itself. So I'm going to divide both sides by 3. Now I have 1024 equals 2 to the n minus 1 power. To get that outside, or to get that variable to help it escape from that exponent, is if I write it in logarithmic form. So I'm going to rewrite this as log base 2 of 1024 equals n minus 1. Remember, there's a trick that we can do. You could plug everything on the left into your calculator. Log base 2 of 1024 is 10. Then we solve for n here. I see that n equals 11. So that's my number of terms. So now finally, I just plug everything in. My a1 value is 3, r value is 2, n value is 11. Let the calculator do the work. That sum would be 6,141. So again, I'm taking every value in that geometric series and I'm adding it all together. So the 3, the 6, the 12, the 24, all 11 terms that go all the way up to 3072. That sum would be 6,141. Let's look at one more example, but here you're given it in sigma notation. So it looks like I'm going from the 0 to 20. For my n value, and my explicit formula is 4 times 1/2 to the n power. Again, I'm going to use my formula. To find my a1 value, what I'm going to do is plug in my lower limit. So my a1 value, I'm going to plug in 0 because that looks like that's what I'm starting with. So 4 times 1/2 to the 0 power is just 4 times 1, which is 4. So I'll plug that in. Just looking at this, I can see that my r value is 1/2. So I'm going to plug that in for r. And finally, to find my number of terms, remember you do your upper limit minus your lower limit plus 1. So I'm doing 20 minus 0 plus 1, which gives me 21. So again, from here, at this point, you just let your calculator do the work. My answer here would be about 8. So the next thing we're going to talk about is an infinite geometric series. So these ones are a little bit trickier to picture. An infinite geometric series with the first term of a1 and a common ratio, absolute value of r is less than 1, actually has a finite sum. And how you would find that finite sum is you would do your first term over 1 minus your r value. So what I mean here is that I don't have an a sub n term. I start with my first term and it's going on for forever. And depending on what your r value is, you could keep adding a value that gets smaller and smaller and smaller to where you end up kind of having a finite sum there. And that's the formula of where you would figure it out. On the other hand, though, an infinite geometric series with an r value greater than 1 will not have a finite sum, or important here, in our absolute value of an r value greater than 1, because it could be negative. If that value is greater than 1, not going to be a finite sum. When we do have a finite sum, we consider that series to converge, and when it doesn't, we say that it diverges. So let's look at 2 examples that way. Here, I want to ask, does the following series converge or diverge? If it converges, what would the sum be? In example A, we see the start of a series, 1, then we go to 1/2, then to 1/4, and then those ellipses at the end indicate that I'm going on for forever. So again, I don't have a final term here. So to figure out if it converges or diverges, I want to focus on my r value. So it looks like going from 1 to 1/2, I multiply by 1/2. That checks out because going from 1/2 to 1/4, I'm multiplying by 1/2 again. So my R value is 1/2 or 1/2. The absolute value of 1/2 is less than 1, so I can confirm that this converges. Finally, to find the sum, I use that formula. So my first term, 1 all over 1 minus my R value, which is 1/2. That sum will be about 2. So that's my sum for the series. And this might seem a little bit weird that if you're having if you have an infinite series that you would have a sum. We'll talk about this a little bit more in class in more detail. In example B, let's look at something with summation notation or sigma notation. If you have an infinite series, notice it'll have that infinity sign where you would have your upper limit, because again, I don't have an upper limit really here. Again, I really just want to focus on my R value. Here, my R value would be -5/4. Since the absolute value of -5/4 is greater than 1, that series would diverge, so I don't have a sum here. Finally, last problem that I want to talk about today is like a real world problem. I think that sometimes when you talk about geometric series, the numbers get so crazy and big really quick that they're kind of hard to picture and they almost seem like they're not real. So I'll show you one example of what I'm talking about here, and that'll finish up today's video. Let's say you and a friend are playing Mario Kart and you guys place a bet with each other. So whoever loses will have to pay the winner 1 cent every day for the entire month of April, and then you double it. So what I'm talking about here, so if you win in Mario Kart between you and your friend's going to pay you 1 cent on April 1st. Then on the next day, they're going to double that, so you'll get 2 cents the next day. Double that, you'll get 4 cents the next day. Day after that, double that, you'll get 8 cents, and that's going to be how the pattern goes for the whole rest of the month. So with that bet in place, how much money would you be making at the end of the month? So I'm going to be adding up everything that you earned from April 1st to April 30th. So this might not seem like a lot because we're starting with 1 penny and we're only going for the month of April, but you're going to see that over time, especially since this is a geometric series, our numbers are going to get really big really fast. So if we want to find the sum of how much money you're going to make, let's plug in what we know. A1 is going to be 1 because, again, you're receiving 1 penny on day 1. So we'll keep everything in cents for now. We'll convert it to dollars in the end. Our R value is 2 because we're doubling that amount every day. And finally, your N value is 30 because there's 30 days in April. If we plug this into our calculator, we get this crazy, giant, huge number, which again, you might be thinking, oh, okay, well, this is just pennies. What would this be as dollars? If I divide by 100, you end up getting $10,737,400 if you win this bet, which seems crazy because, again, you're starting with 1 penny. But when you're multiplying each time, that's exponential growth there, and we're adding everything together, that number gets really, really big.